I'm going to draw pictures to try to show what's going on here. We're going to have the Earth. Let's make it blue. And we have a telescope that starts on the surface of the Earth. And then we're going to want to put it into orbit. So on the right side of the page, there's the Earth. Now we're going to have this telescope, but it's orbiting the Earth in, we'll assume, uniform circular motion. So we're asked in part A and part B to calculate the change in gravitational potential energy of the telescope as well as the change of kinetic energy. So in the first scene, the starting speed of the satellite is 0 meters per second. Okay, so it's actually got 0 kinetic energy at the start. And in terms of gravitational potential energy at the beginning, we're going to use the formula for gravitational potential energy, but the distance is going to be whatever the radius of the Earth is. Okay, that's how far the telescope is from the center of the Earth. It's whatever the radius of the Earth is, which we can look up in our document of useful values. The radius of the Earth is 6.38 times 10 to the 6 meters. Also, to calculate gravitational potential energy, we're going to need to know the mass of the Earth, which is also in our document of useful values, 5.98 times 10 to the 24 kilograms. We'll also need the mass of the telescope, which is given in the question, 11,000 kilograms. This is close to the actual mass of the Hubble Space Telescope. I just used values that were rounded a bit more, just to make them easier to write down. Okay, so that's the first scene. The telescope just at rest on the surface of the Earth. Okay, then it gets launched, and when it gets launched, it's now got a height of 540 kilometers above the surface of the Earth. But how far is that from the center of the Earth? Okay, how far is that from the center of the Earth? I'm going to call this R2, the distance of the telescope from the center of the Earth. That's going to be the radius of the Earth plus the additional 540 kilometers. Okay, so the radius of the Earth was 6.38 times 10 to the 6. And 540 kilometers, when you convert that to meters, that ends up being 540,000 kilometers. Which is equivalent to 0.54 times 10 to the 6. Okay, so adding those two together will actually give me 6.92 times 10 to the 6 meters. So that's the distance of the telescope when it's in orbit from the center of the Earth. Now it's also going to have a different speed. When it's in orbit, it's going to have a different speed. And that will have to be calculated. We're doing that in part B, and we're going to have to use unit 1 and 2 formulas to do that. Okay, so there's the setup. We have a before and we have an after. We're going to calculate the energies before, we're going to calculate the energies after, and we're going to see the difference. And that's going to represent how much energy we have to invest into getting this telescope into orbit. All right, so I'm going to start a new slide then. Part A, calculate delta U. calculate the change in gravitational potential energy. That's going to be the final gravitational potential energy minus the initial gravitational potential energy. And that's going to be just applying the formula for gravitational potential energy. Which is a little awkward because the formula for gravitational potential energy has a negative sign in it. Okay, so there's the final potential minus the initial potential energy. I could just plug the numbers right in there, or I can actually do some common factoring. Both of these terms have negative GMM in it, so I can common factor that out. When I do that, I'll be left with 1 over R2 minus 1 over R1. Okay, and now I'm going to evaluate that. There's a universal gravitational constant. Now the mass of the Earth. Now the mass of the telescope. And then 1 over the second distance. So that's what we calculated as 6.92 times 10 to the 6. Minus 1 over the starting distance, which is the radius of the Earth, 6.38 times 10 to the 6. Okay, I'm going to try to put that all in the calculator without making a mistake. So wish me luck. Okay, so I think I got it 5.37 times 10 to the, okay, let's count decimal places here, times 10 to the 10. So this would be in joules. This is gravitational potential energy. So this is the change of gravitational potential energy to lift up this telescope by 540 kilometers above the surface of the Earth. I'm going to need this value when I do part C and D, so I'm just going to make a note of it so I don't forget it. Okay, part B asks us to find delta K, the change of the kinetic energy of this telescope, which is going to be the final kinetic energy minus the initial kinetic energy. In this case, this telescope starts at rest, so the starting kinetic energy is 0. So I'm just finding the final kinetic energy, which is going to be half mv squared. So I need to know the mass of the telescope, which I know what it is. It's 11,000 kilograms. That's what the question stated. And I'm going to need to know the speed of this telescope. And that's where I have to go back to Unit 1 and Unit 2 material. So going back to Unit... I think it was Unit 1, we do have a formula for the orbital speed. Okay, we do have the formula for the orbital speed of a satellite or anything orbiting a planet. So let me go back and try to look up that formula. or I'll go onto our formula sheet actually. Okay, so the orbital speed formula is square root of gm, okay, that's a capital M, over r. Okay, so I'm going to apply that to find the speed of the satellite. Actually, I'm going to square it first, because now I can make a substitution into finding my kinetic energy. Okay, so it's going to be 1/2 times the mass of the satellite times g capital M over r. This will be 1/2 times 11,000 times 6.67 times 10 to the negative 11 for the universal gravitational constant, times capital M would be the mass of the Earth, and r would be the distance between the telescope and the center of the Earth, which was 6.92 times 10 to the 6. Okay, so I'm going to try to calculate this. Okay, so that's giving me 3.17 times 10 to the, let's see, 11 joules. So that's how much kinetic energy this telescope has now. It started with 0 joules of kinetic, now it has 3 times 10 to the 11 joules of kinetic. I'm going to make a note of that value because I'm going to need it in the next part. Okay, part C. They want us to add up those two answers to part A and B. They want us to add up the change of gravitational plus the change of kinetic. So I did make a note of what those two values were, so I can add it together. This will end up being 3.71 times 10 to the 11 joules. Okay, so that's the answer to C. If I didn't make a mistake, I did mental math there. Part D. So if it says if 1 kilogram, I think. Yeah, so if 1 kilogram of fuel gives us 1.2 times 10 to the 8 joules of energy, how many kilograms of fuel are we going to need to reach the answer from part C, that much energy that we calculated in part C? So that's going to be a division. So 3.71 times 10 to the 11 joules is the amount of energy we need. We'll divide it by this conversion factor. And we're going to need 2,641 kilograms of fuel to two significant digits. So that's a lot of fuel. That's how much fuel we need to have enough energy to put this into orbit. Or do we? Part E asks, why is the answer to part D just a tiny fraction of the actual amount of fuel needed to get the telescope into orbit? So we actually need way more fuel than 2,641 kilograms. And that's because not only do we have to use energy to put the thing into orbit, we need to use energy to lift up the fuel that's being burned. Like the fuel has its own weight, so we have to use energy, like it's going to weigh down the rocket. The rocket also has weight, like we have to attach this telescope onto a space shuttle and get the space shuttle up there before we can release the telescope. So we're not just lifting up the telescope, we're lifting up the space shuttle that's carrying up the telescope. And burning of fuel is not going to be 100% efficient anyway. 1 kilogram of fuel may contain that much energy, but we don't get 100% of that energy because we're not going to be 100% efficient. So lots and lots of reasons why we're actually going to need way more fuel than what we just calculated there. So fuel has its own weight. The shuttle carrying the telescope has weight as well. And burning fuel is not 100% efficient. And these are just 3 reasons. There are likely many more.